Hey guys, welcome to this video. In this video, we'll discuss about an interview problem, and this problem actually involves a little bit of concepts from mathematics, from calculus to be exact. You will understand as how we'll try to apply this in small measure in this video. So let me state the problem. So you're given an array, and the array is
5, 2, 6, 7, 1, 3. And what we have to do is,
you have to visualize it in a different fashion now. You have to think of it as some kind of a wall of height 5 units, of height 2 units, of 6 units and 7 units, and then 1 unit and 3 units. Now the problem, what it demands as an answer is, you have to find out how much unit of storage can be done in between these two walls. So this amount of storage, this value in unit we have to calculate. So in this case, this is 5, this is 2 and 6 and 7, 1, 3. So 5 and 6. So if you take how much unit can be stored in this particular area, it is 3. So 5 minus 2, it is 3. In this case, it is 3 minus 1. We can store 2 units. So essentially 3 plus 2 can store 5 units. So we have to write a code that will give us this result. That is how much unit of rainwater in this context we can store in between these given values. So guys, I'll give you a few cases to better understand the problem. If you're interested directly in the approach to solve this problem, you can skip the next 30 seconds or so. Anyway, let's start with the approach. So let's say you're given an array whose value is 2, 1 and 2. So let's try to visualize it. You have a wall of height 2 and then a wall of height 1 and 2. So how much unit of water can we store in between this? So just by a visual inspection, we can say we can store 1 unit of water right in between these two walls. So actually, in order to say that, our brain has done two important jobs. That is, first thing is we eliminated an opportunity, that is, we know that these borders cannot store any amount of water for us, because we know in any vessel, let's take any vessel, the border is not going to help us store any resources. It is what is inside that helps us store value. So we'll start from here. So this is one takeaway from this particular case. And the other is, we looked to our left side and then we observed our right end. And we said, you know what, I have a wall of height greater than the present element, and even in the right, that is the same case. So what I can do, I can just subtract the height of the wall 2 and from the current wall height. So 2 minus 1, I'll get 1 unit. That is yet another case.
if you are given an array which has these values, which is 3, 1 and 2.
Alright, so let's try to visualize it again. We have a wall of height 3 now and a height 1 here and 2 here. Alright, how much can we store? We can store 1 unit. Even in this, just by visual inspection, we can store 1 unit of whatever resources that we can store. But in this case, the decision was a little different. The first inference was applied, that is, the borders can be eliminated. We can start from the middle element. The second one, we have to add certain more information to it. That is, we have to look at our walls, both of these walls, 3 and 2, and find the minimum in this case. So 3 and 2, if we take the taller wall, then we cannot store any resources here, because this right wall will not support such case. So this has to be eliminated. So in order to do that, you have to find the minimum between these two. In this case, 2 is the minimum, and from that you subtracted your present wall height, which is 2 minus 1, which gave you 1 unit. So by putting all these cases, what you understand essentially is that you cannot take a decision based on the local information. That is, you cannot take a decision how much water I can store by just looking at the next element or the element to the left. So I'll better explain this point in the next one.
Alright, let's take this case where you're given an array and the values are 4, 1, 2 and 4. Alright, again let's try to visualize it. We have a wall of unit 4, 1, 2 and again 4. Alright.
So in this, if we follow our conventional approach, that is, alright, we neglected the borders, and right in the first element we look at the information of our neighbors. We ask our left, hey, what's your height? He says, I have a height 4. And you look at your right neighbor and you say, what's your height? His height is 2. So based on this localized information, if you try to take a decision as how much I can store, definitely you go for the minimum one. In this case, the minimum of these two is 2. And from that, what you will do is you will subtract your present height value, which is 1. So you will get a value of 1 unit, which in fact, if you see from a global perspective, you had a case where you could have stored more in this case. So here you have 1 unit and then this height was 4. So you had 2 units which could have been computed at this present value. Because at the right, you have a wall which has a height 4, which facilitates you to store a higher value. But what you did, you took a decision based on your neighbor. So in this case, what we should have done is, we should take the information of the global maximum value on our right side. That is a global maximum on our right side. And the global maximum on the left side. So if we take decision based on the global left and max, then here in this case, what we'd have done, we'd have asked, what is the global max towards my left? 4. Global max to the right is 4 again. So minimum of both those two is 4. So 4 minus 1, I could have stored 3 units. Now that is correct answer. In this case, global maximum to the left and right is 4. Minimum of both of them is 4. 4 minus 2, you will get 2 units. So if you add them, you'll get a result of 5 units. Alright. Now let's consider an actual test case. So the first step is to start with the iterator. So we'll point our iterator to the second element, since we know the border elements does not comes into the calculation. So we'll start from here with the wall of height 3, and what we have to do is, now the repeating process, if you see, the first step is to calculate the largest element in your left side and the largest element on your right side. So largest element on your left side, I'll call it left, and the largest element on your right side, you can call it right. Alright. So in this case, the largest element on its left is 5. We have just one element here. In this, out of 6, 4, 6, 3, the largest element is 6. So right is 6. The third step is to find the minimum between this left and right. Right. And this value, from this value, we have to calculate how much we can store at the current index. But before that, we have to check one condition. If the value, so I'll define value as the minimum of left and right. I'll call it, let's say this is x. So x minus the value pointed by the current element I. So array of I, that will be my value. So that value, if it is greater than 0, I will include it to my result. So result will be plus equal to value. That's a shorthand representation. And so if this case is met, then I will update the value of result, and result will be returned from this function. So this will be my kind of a pseudo code. This will be the repeating steps. So let's try to solve this problem, what exact values we get. So in the first 2 steps, I have done 5, and out of this 4 element, 6 is the largest element. Minimum of left and right in this case is going to be 5. Alright. And now if you take that 5 and subtract it with the array pointed by the iterator I, we have element 3. So 5 minus 3 is 2. So is 2 greater than 0? Yes. So what we will do, we will update our value of result to 2. Initially it was 0. Initially we'll set it to 0, and now it's 2. Now, in the second step, we have to repeat the same step, but we have to increment our pointer. Now our pointer will point to sixth, that is the third element, whose height is 6 units. Now, if we take that, we have to calculate first the the largest value towards its left, and the largest value on its right. So on its left, we see the largest element is going to remain to be 5. So we have to compare between 5 and 3. 5 is larger. So in the right, we have to compare with 4, 6 and 3, and the largest value is 6. So 6 is retained. Now the minimum value will be again 5. And if we subtract 5 from 6, now you will understand why I have included this condition value is greater than 0. Because check it out, the minimum value is 5. Now the array value is 6. Okay. Now if you find value, it is 5 minus 6, which is equal to minus 1. So minus 1, definitely that means, what it means in the physical realm is that we cannot store any amount of, we cannot store, or it cannot store any amount of water in our context, if we call it a rainwater problem. So this will be neglected. This step will be just like, if it is not greater than 0, we will not update the value of result, and again we will repeat. Now we'll increment our pointer so that it points to our fourth element, that is of height 4 also, and we will repeat the same step. On our left, what is our largest value? Now in this case, our largest value is going to be 6, and on our right, what is our largest value? Again 6. What is the minimum of both of these value? Minimum is also 6. 6 and 6, minimum is 6. All right. If the value is x minus array of I, in our case, the value will be x is 4, x is 6, and array of I is 4. So we'll get a value of plus 2, which is greater than 0. We'll update the value, we'll increment this value. So 2 will now be changed to 4. Again, we'll increment this pointer so that it points to 6, and we'll see what is the largest value on our left. Largest value is 6, right? We have a largest value of 3 this time. So what is our minimum? Minimum will be 3. So if we find what is our value will be equal to 3 minus the array value. Array value is 6, which we will get minus 3. So is it greater than 0? No. So result will be retained. So after crossing this, borders will not be involved. So borders we will not include in our computation. So we'll stop here.
Alright, so before we code the solution to this problem, let's talk about its time complexity. So given array was 5, 3, 6 and then 4, 6, 3. This was our given array. And now in this given array, what we have to do is, first we initialize a pointer, then we calculate the global minimum towards our left. So in the left direction. And on our right, we calculate the minimum. So what we have to do at each step, we traverse, in order to find the maximum element on our right, we have to traverse all the elements, all these elements. And in left, also we have to traverse all the elements which is on our left side. So at every stages, at every point, first we have to traverse all these elements when we come to one particular point, from there again we have to traverse almost n elements again. To calculate the leftmost maximum and the right maximum, we have to traverse all the elements in our left and right. So again we have an n. So n into n, we have an n square problem. So whose time complexity would be order.
Alright, so I have taken the driver program and now we'll write this function rain trap, which accepts an array, that is our test case, and the size of it. So first, as we discussed, first would be we'll initialize our result initially to 0, and then we'll open a for loop since we have to iterate over all the elements, leaving the borders. So I'll start from 1 and I'll leave the final element. So I'll traverse till the element before the last element. So increment it at each stage. And now within this repetitive steps, I have to perform, the first step is to find the left. So I'll start it and give it a initial value of I minus 1. So on the left side, and then I'll have to update the value. So in order to find the largest value on the left, I have to traverse all the elements in my left. So I'll start from int j equals 0 till j is less than I, and I'll increment j plus plus. Now my left value will be the max between the existing left value and the new value, that is array of j. Alright, so after this is done, we'll have to do the same step, but now we'll do it on our right side. So int right, I'll assign a value on the right, that is I plus 1, and we'll have a for loop to iterate over all the elements on our right side. So int j equals, it starts from I plus 1 and it has to end in an element which is before the last element, so less than n. I can increment j, and my right value will be the max between the existing right value and the array value pointed by my iterator j. So now that I have the left maximum and right maximum, I can just update, but before that I have to calculate a particular value that I can define as the minimum of this left and right, minus the array value pointed by I. So, and I have to check if that particular value is greater than 0 or if it is positive. If it is positive, then we'll add it to our result. So result will be plus equal to val. Alright, now after this for loop, what we have to do is just return our result. Now that will be taken into this function rain trap and we'll print it. So alright, now let us run our program, and let's see what result we get for this current. We should get an answer of 4, and exactly we've got this answer. So you can use this code, and in the next section we'll see how we can optimize it.
Alright, now to optimize our given solution, what we can do is, instead of calculating our largest point in our left side and right side at each point, we can store it in our arrays. So we have to spend some amount of memory and do some linear work in order to reduce that big overhead of calculating left and right at each stage. So what I'm trying to say is, we can store the largest value in this array. So first case, in our first element, what is our largest element? Our largest element was 5. Just we can compare only with 5 now. Now in this case, 5 and 3, our largest element is again 5. If you compare it with 6, 5 and 6, the largest element is 6. 6 and 4, again 6. 6 and 6, again 6. 6 and 3, again 6. So from left to right, we'll write the maximum element. In this case, from right to left, we will write the maximum. Here in this case, it is 3. And next 3 or 6. 6. 6 or 4, 6. 6 or 6, 6 again. 6 or 3, again 6, 6. Alright. Now we'll repeat the process as we have discussed in our earlier section. We'll start from third step, that is, we'll calculate our value. Now in this case, how we'll calculate is, we'll calculate the minimum in this first value. So let's say we are starting at this first index 3. What we'll do is, we'll have to take the minimum from this array at the given same index. So if this index is pointing to first index 1, if we start from 0, then in the first index we have to, from left to right matrix or left to right array, we get a value 5, and in right to left we get a value 6. Between these two we have to calculate the minimum, and that particular value will be subtracted with the array value pointed by I. Now in this case it is 3. So minimum of 5 and 6 is 5. That will be subtracted with 3. We will get a value 2, which will be stored to result, which can be used to update our result. And now we'll increment our pointer again. This will point to second position, second index, and then if we do the same process again, calculate the minimum between 6 and 6. The minimum is 6 again. So 6 minus array value is also 6, which is 0. There will be no change to our result. Now if we increment again, go to 4. If we do, we have to first calculate the minimum element. So minimum between this 6 and 6 is again 6, and the value, array value is 4. So our value is 2, which is greater than 0. Now we will update our result. So 2 plus 2 will get 4. Now we'll have to increment it again to 6. The minimum value between 6 and 6 is again 6. 6 minus 6 will be 0. So no change. Now in the borders, as we have already discussed, it will not be taken for consideration in our computation. So with this, what we have done is we have a 2 array. So we are spending some amount of memory, but the good news is that it is linear. So what we were trying to do initially was, if we go to this point, we'll traverse all these 4 points and all these points in the left side and calculate the maximum value on our right and left. At each stages we do that. So we had a complexity of order of n square. In this case, since we have stored the value, we have done a linear amount of work in order to calculate this maximum value. But anyway, the complexity is reduced to order of n, but the space complexity has also increased to order of n. So our space will be order of n and time will be order of n, as opposed to order of n square and order of 1 space initially.
Alright, now let's write the optimized code. The optimized code is quite similar, except we have an array. So initially we'll start with a result equal to 0, and we'll have an array of size n, and another array which stores the maximum from right to left of the similar size right of n. Now we'll initialize a value that left of 0, the first value, will be equal to array of 0, and similarly we want our right value, in our right array, the rightmost value, that is given by n minus 1, to be equal to the array's last element. So we'll initialize the last 2 points in our array. Now you'll understand why we do so. So we'll have a for loop to start from I equal to 1, I is less than n, runs till the last element, and we'll increment it at each stage, and our left of this present value, that is left of I, will be a result of maximum between the array element, which is one element before the current element pointed by I. So it will be the element before ith element. So in this case, in the first iteration, if I is equal to 1, now left of I will be I minus 1. So we'll compare it against one element behind this particular element, and we'll compare it with the present element, and the maximum will be stored to that array. The same step is done for the right one, except that int I, it will start from the reverse, that is from the behind or from the last element, and will come from last element to the first element. So our initial point will be n minus 2, since we are starting from the last element, last before element actually, and till it is greater than or equal to 0, we'll continue this process, and in this case we'll do I minus minus, and we'll store our right value. That value will be the result of maximum between the right value of the previous element. So since we are coming from right to left, we have to see in I plus 1 and the array of I. So if we store all this value, now we have the left maximum and right maximum in our left and right array. Now we have to just do we have to find the result by running through all these elements. So int I is equal to 0, I is less than n, I plus plus. Alright, our result will now be equal to the minimum of the left element pointed by I and right element at I minus the array's present value. So this step is similar to the previous one. We'll just add a bracket here, and then final step is to return the result. All right, now observe that we have done linear amount of work 3 times. So it is we have traversed entire array here once, and again here once we have traversed the entire array, and again to calculate the result we have traversed the entire array here. So it is much better than n square, but we have another solution where we don't have to store this array in a we don't require an array to store all these values. We can just have a stationary variable that can keep track of our left maximum, right maximum. So anyway, this is much better than the order of n square result. Let's try what solution we get. For this current test case, we should get a solution of 4 units. Let's see what we get. Yes, we get an answer 4. So this is about our code.